So atomic mass. So if atoms of the same element can have different numbers of neutrons, then they have different masses, and that means that part of Dalton's theory was not exactly correct. Doesn't mean we have to discount the whole thing, but it means we need to modify that part of the theory. So different isotopes of a given element do have different masses, but they all have the same number of protons. So since we do experiments with gazillions of atoms, we are interested in the average mass, not in the mass of an individual atom for the most part. So the average mass is called the atomic mass. That is the mass of an atom. It's the average mass of an atom. So the average mass of a chlorine atom is 35.45, and we use the unit atomic mass unit.
Is it the atomic mass of like all the different atoms that we know exist, or is this?
Yeah, good question. So this is the mass, the average mass of all of the different isotopes of chlorine in their natural abundance. And we're going to learn how we calculate that. So just like if you had two children, one's age 10 and one's age 12, their average age is 11, and yet neither of them is 11, right? So you could say that, well, there's normal, which is an average of what people are, but nobody's actually normal, right? So that's the average mass. It's very useful to us, but it's not the mass of any of the carbon atoms. It's the average. So it's calculated based on natural abundances. So if we look at chlorine, 75.77% is chlorine 35, and the atomic mass of chlorine 35 is 34.97 AMUs. This number, the actual mass of the isotope, is going to be very close to the mass number. It's not going to be exactly the same, though, except for carbon 12. And if you want to know why, I can explain that to you outside of lecture. 24.23, the other part of 100, is chlorine 37. Their mass is 36.97 atomic mass units. So to find the average, a regular average, a simple average, you take all the values and add them up and divide by the number of values. When you've got gazillions of atoms, you don't have time in your lifetime to do that. So we use a weighted average, not unlike the weighted average I use to calculate your grades. So like your exams, I think, are 45% of your grade. So like this percentage, you take that and make it into the decimal form. 75.77 becomes 0.7577. This is the, when you calculate a percentage, it's the part over the whole times 100. So what we're doing here is we're using the part before you multiply by 100. It's this much times the mass, and for the other isotope, it's percentage made into a decimal times its mass, and then you add those together. That's what happens in a weighted average with your grades. We take your exam average times 0.45, and your homework average times 0.1, etc. And you add those together and you get your average grade. So we add these together and we get 35.45, the average mass of chlorine. So let's do an example of calculating an average atomic mass. So I'll give you this clue. When we're doing it for an actual element, you can check your answer because it's on the periodic table. And I am aware of this, and so on an exam, my favorite thing is to give you a made-up element, right? So you can't check it and just write down the answer off the periodic table. Okay, magnesium has 3 naturally occurring isotopes, masses of 23.99 AMU, 24.99 AMU, and 25.98 AMU, and natural abundances of 78.99%, 10.00%, and 11.01%, respectively. Calculate the atomic mass of magnesium. So this word respectively means that this list of 3 numbers, 3 masses, and 3 percentages they're both in the same order. So the first one of this list goes with the first one of that list. So what we do is we take the percentage and make it into a decimal form, dividing by 100. So 78.99% becomes 0.7899. And we multiply by the mass of that isotope. So that one goes with 23.99 AMUs. And then we add the next one. 10% becomes 0.1000. And that one is 24.99 AMUs. And the last one, 0.1101 times 25.98 AMUs. We're doing a weighted average. So we just get it off the calculator and we punch them in just like that, 7899 times 23.99 plus. I'm not going to read the rest of that to you. And that's what my calculator is giving me. 24.309099. Anybody else get that number? Yeah, thanks. Should we use all of those digits? No. We should follow the rules of significant figures. Here's my opinion about significant figures. We should know how to follow the rules and be perfect with significant figures. And there will be questions on the first exam that are specifically testing you on your knowledge of significant figures. After the first exam, we're just going to say, well, let's be reasonable with our significant figures. Let's try, but I'm not going to give you, mark an answer wrong just because you've got one too many sig figs or one too few. I'd like you to remember that it's always best to have too many because you can knock them off later, no problem. If you have too few, you can cause some pretty serious rounding errors. So here we could look at the multiplication and the addition together and figure out precisely how many significant figures that should have. Anybody feel like doing that? I don't. Or we can look at this and just kind of say, well, what would be reasonable? 4. This has 4 sig figs. That one has 4 sig figs. But there's adding involved too. This one has 2 decimal places. All those masses have 2 decimal places. If I round this to 4 significant figures, it's also going to have 2 decimal places. So that's probably correct, and it's definitely reasonable. So I would round that to 24.31 atomic mass units. I do like boxes or circles around your final answer. Somebody asked me because they had a calculus instructor who hated that, right? Didn't ever want you to put anything around your final answer. So this is a life lesson that we learn. You find out what the person who has authority over you wants, and you do your best to give that person what they want within reason, right? So I'm not going to be militant about this, but it makes it easier for me to grade your papers if you clearly identify what's your final answer, because sometimes it's all squirrely all over the place. And if you put a box around it, I can look at that, and if I see work and the correct answer, I can go on, and I don't have to look at the rest of it. So magnesium, periodic table says 24.30351. Well, ours is 24.31, but that one rounded would be the same, so we probably did it correctly.
They just got that number just to calculate it to a way longer decimal, probably.
Yeah, that number on this periodic table was used with, calculated using more precise masses. Yep. Yes, and so that brings up a great question. How many of these digits on these masses should we use? It is always correct and acceptable to use all the digits on whatever periodic table you're using. Some of them have more than others, and the average masses are revised occasionally, and so if you have an older periodic table with precise masses and a newer one, those last couple digits might be a little different. You don't need to worry about that. For a general chemistry class, most of what limits the number of significant figures in our answers is the number we're starting with, the measurement, and it typically has 3 or 4 significant figures. So if we round our atomic masses to 4 significant figures, that usually doesn't affect our ultimate answer in the problem. And some books give you a periodic table where they're all rounded to 4 significant figures. So most of them will have 2 decimal places, some will have 3 decimal places. And so that is also entirely fine. I taught out of a book with a periodic table like that for so many years that I have a whole bunch of the molar masses, atomic masses memorized with 4 sig figs. And so I will use 4 sig figs in lecture. And it should agree with those numbers on the wall, rounded to 4 sig figs. You're always welcome to use all of those. What's not okay is to round to fewer than 4 sig figs. Sometimes people just round to the nearest whole number. Well, for this one, it'd be 24. Well, 24.3 and 24, and for chlorine is 35.45. That's almost right in the middle between 35, and 36. And so you round that to 35, and you can get some pretty significant rounding errors. So don't do that. Do not round to the nearest whole number. Don't do that. 4 sig figs on the molar masses or more. Any questions about that? Occasionally we do this like really rough and dirty, just kind of estimating calculation where you might just use rounded ones, but that's just kind of to figure something out real quickly, and we usually don't even write that down, and so I will never ever do that in lecture. $24.31. How do they measure these masses? Using a mass spectrometer. So here's a diagram illustrating how a mass spectrometer works. And I'm not going to test you on the workings of a mass spectrometer. That's for a different class. But I'd like you to have heard about it and just have a clue of how this works. It's really kind of neat. So what happens here is the sample is injected into the instrument, and there's a heater here that vaporizes it. You can turn anything into a gas, even metals. And so it's vaporized because then it can move through the air, unlike a solid, which tends to sit in a lump. So we've got it in the gas state now. We bring it through here, and we shoot electrons at it. And some of the electrons stick, and so we get charged particles now. Charged particles are nice because we can use an electric field to accelerate them. And so we use this electric field to accelerate these particles, get them going faster, and then we take these charged particles through a magnetic field, and the magnetic field is going to bend their path. The path gets bent depending on how heavy they are. The heaviest particles have their path bent the least, and the lightest particles get bent the most. And so by looking at where the particles hit on the detector and doing some, calculations that the computer of this instrument does for us, we can identify what the masses of the individual particles are. Very cool. So the output would be something like this graph over here, where it gives percent intensity and different masses. So this one has a mass of 107, this one has a mass of 109. This percent is a percent intensity. It is not the relative abundance, right? Because 100%, and that looks to be about 93%, that doesn't add up to 100. So that can't be right. Actually, these two are close to the same. It's close to 50-50. They're almost the same abundance. So you have to take the intensity and normalize it to 100%. And if you're interested, the calculation is here. We end up with 51.84% and 48.16%. Again, I'm not going to test you on that either, but just so you know, I understand that this is not 51.8%. It has to be normalized.